Yeah, no worries. I'm trying to
5 minutes, okay. Oh,
whenever you want to chat.
I think that's really interesting for like,
okay.
Yeah. Use that as like a gate.
Before and after.
Absolutely.
Yeah. Okay.
Cool.
Good morning. We're going to go ahead and get started. My name is Kira Larson. I'm the Education Program Manager in the Stanford Center for Clinical Research. We host these lectures and presentations that we call the Science Series every month, except for next month. We're not holding one, but we'll be back in August with Dr. Matt Baker, who will be presenting on some basics in immunology and rheumatology. And then for today, we are doing something a little different. I teamed up with Steve Torsha, who is the project manager in the Center for Digital Health, and wanted to talk more about this newer center at Stanford, as well as some of the new projects that they are doing. And this was a good way for us to collaborate, and hopefully that continues, and we work together on more future projects and presentations. So with that, I'm going to turn it over to Steve to talk a little bit more about what the Center for Digital Health is, what they do, and some of their areas of focus and current projects. Thanks. You want this or?
All right, good morning, everyone. Can you hear me all right? So, thanks all for joining us. This is a unique one, combining with the SCCR, but I'm excited to give a few minutes to talk about the center. And some folks may not know, I want to start with this goofy looking slide with a guy looking very Star Trek-y about what is digital health. I'd like to ask folks what is digital health, because nowadays it's become quite a murky term. Anyone want to give their 2 cents? Any definitions? So for me, I kind of like to think of it as intersecting technology and medicine. And digital health nowadays, you can have a lot of different apps, data, analytic platforms, wearables, sensors, and all over the place, different things that you can use to apply to particular clinical areas with the hopes of increasing outcomes. So the Center for Digital Health, we started in January of 2017, a relatively new center here, and while we are a new center, digital health is nothing new to Stanford. Folks have been doing many great things across the ecosystem here. So we are one of several centers, and our purpose is really to enable, connect, and to lead particular initiatives. So this is a little bit on our team. We're championed by Dr. Bob Harrington. He's the chair of the Department of Medicine. Minty Tarakia, a cardiac electrophysiologist. He's our executive director. Ewan Ashley is our head of technology and science, and we have a great team, including a few in the room. So our center, we really try to connect the Stanford University ecosystem even beyond the School of Medicine. So we try to interface the best we can with the School of Business, you know, the D School, the Design School, and the School of Engineering. And so really our purpose, we try to break it down simply: enable, connect, and lead. So we try to enable the School of Medicine community to learn and more and source and manage and promote digital health activities. And then we also try to connect internal School of Medicine community to the external opportunities outside of Stanford, as well as we lead and develop particular projects, which I'll get to in a minute. So to enable our community, back when we launched in 2017, we sent out some great surveys to faculty and researchers to understand what their needs are so we can try to support them. And we did this in a few different ways. One was providing guidance resources and tools to launch digital health projects. It's quite complex here at Stanford and other places. When you have to launch projects, you have to go through data privacy and security and so on. We also tried to get a landscape analysis of the expertise within digital health at Stanford. So on our website, we have a database of digital health leaders and experts. We also hold events like this, like workshops and events as well. So quick shout out, I'll breeze over this about workshops that we do here, not just educational workshops like this, but also in-depth information like an elective course. We just wrapped up here. It was a 2-week elective course for internal medicine residents. We also had some non-internal medicine residents, and we had great speakers come and talk about career path, mentorship, understanding, do you want to get into academia, do you want to go to a startup, things like that. And like I mentioned before, we also connect external and internal folks to people here at Stanford. So we really try to be that connector and not overlap with other centers and initiatives. We also lead strategic initiatives, things like the Apple Watch Seed Research Grant, which I'll get to in a minute. We also play a role in My Heart Counts, the Apple Heart Study led by SCCR, and we also do our educational programs as well. So the Apple Watch Seed Research Grant, which we have a couple folks here with the teams that I'll introduce in a minute, we received some Apple Watches. We had a whole request for proposals where we really crowdsourced great ideas and tried to select the few winners. So we have one here today, and we were able to, be able to score them, notify the awardees, and try to get these devices into the hands of the researchers, because that's really what our center is all about. And here's a quick shout out to the 5 winners, one of which I'll introduce in just 1 minute here, Lorene Nelson and her project team on individualized migraine attack prediction with self-reported passively collected data. And my slide deck keeps moving without me. Clinical research, so My Heart Counts. I'll briefly touch on this. I want to leave the time for the other folks. Dr. Yu and Ashley's, this project's been ongoing. And there it goes again. And so they have the largest and fastest recruitment for a research trial. They had over 53,000 participants, and this slide's a little old. It's actually more than that now. And they have a great way where you can enroll in this study now. There's also a phase 2 that just came out with their group. We play a role in trying to help promote this and advance it. So it's consistently ongoing. They're improving, and it's a great project. So the Apple Heart Studies picked up a lot of press recently. Our executive director, Mintu Tarakia, is helping lead this Apple Heart Study. It's a separate one from what you'll be hearing today, and it's ongoing right now. And I think at this point, their goal is to enroll 500,000 folks. And you use this, you can find more. I'm not going to talk about it now, but you can find more on the Apple Heart Study online. It's an open enrollment study, so anyone can enroll at this time. So over the last year, we've done a few great things with our limited resources. We distributed over 1,000 watches to faculty. We've held a lot of these educational events, and we try to connect when applicable to these companies that have ideas, funding, devices to the Stanford community to really put them to work and do some cool stuff. And then a last quick shout out of 2017, we do have a monthly newsletter which really outlines a lot of the funding resources, the news, the events, everything from new announcements from the FDA that may impact researchers. We try to consolidate this into a nice format. And then we also do a lot of interesting exploratory requests for proposals, a few coming up this year, so I can't announce anything yet, but it's how we can get resources, whether it be funding, devices, to our researchers. So, and lastly, to external partners, we try to conduct projects when it fits strategically with the Stanford initiatives. We also do the crowdsourcing research, which is one of our Apple awardees we'll speak to in a minute. We also develop tailored education and fellowships, workshops, and even networking events to really try to build strategic collaborations with industry members. So I'll stop rambling here, and let's introduce Dr. Lorene Nelson to introduce her team. Thanks. Good.
Okay, thanks. Okay, hi. So I'm Lorene Nelson. I am an epidemiologist on the faculty here, and I'm also faculty associate director of the Center for Population Health Sciences. A few years ago, I had the idea of developing a clinical research grade app that for the purpose of identifying triggers of migraine among migraine sufferers, from episodic migraine sufferers, with the idea that this kind of technology, if it's useful there, could be also used with other episodic health conditions, seizures, asthma attacks, whatever. So we have a team that's working on this that I wanted to make sure to introduce even beyond the 2 presenters today. We have Catherine Holstein, a doctoral student in epidemiology who's doing her dissertation on this project, and so you'll hear all about that. We have Eric Daza up in the corner up there, a biostatistician who is helping us work on the analytic methods for analyzing N of 1 observational data, and he's with a Center of Population Health Sciences seed grant developing an R program to analyze these data. And then we have Mike Hetal right here to my right, who is an undergraduate student with a vast amount of experience before he even came to Stanford. He has developed the app. You'll hear from him as well. We have Melissa Borghese, who is a master's student and done much of the work on the UI, and Dr. Meredith Barad, who's a professor in neurology and anesthesia and a migraine expert. So I just want to say thank you to the Center for Digital Health because we've gotten not only Apple Watch support, but also just support methodologically, advice-wise, even moral support. We know you have our backs, and we really appreciate that. And also the IRT Mobile Health Server Group has been great, and the DRA group also. So I just wanted to recognize everybody's work in this project, and I'll hand it over to Catherine.
Thanks, Lori. Yeah, thanks for having us here today to share with you our story of mobile health research adventures here at Stanford. So how many of you guys know someone who gets migraine headaches? How many of you guys have migraines yourself? Yeah, lots of hands. And migraines are quite common, with around 6% of men and 17% of women suffering from migraines annually. For those of you who haven't experienced a migraine, sorry, just sticking this in. Thanks. So I'm gonna, I need to turn it on. Okay. Oops. I'm going to start again. All right. For those of you who haven't experienced a migraine, it's more than just a bad headache lasting 4 to 72 hours. It also comes with nausea, vomiting, increased pain with routine physical activity, and extreme sensitivity to light and sound. So pretty debilitating. And one of the challenges in suffering from migraines is the unpredictability of attacks. In general, patients, clinicians, researchers don't have a great understanding of what causes a migraine at one time versus another. And so treatment for migraines commonly takes the form of either acute medications, which may take hours to provide relief once a migraine starts, or daily preventive medications, which require a lot of medication exposure and concurrent side effects. So an increasingly popular idea is personalized migraine prediction on a daily basis with the goal that of targeting behavioral or pharmaceutical therapies at times of highest migraine risk. So what kind of information might actually help us to predict migraines? Well, for one thing, many patients can identify one or more trigger factors that they believe cause their migraines. And the list of potential triggers is long. It's been said that everything is a migraine trigger. Shown here are some of the most common ones, including lack of sleep, perceived stress, weather changes, menstrual cycles, and a number of dietary factors. A few things that are complicating the study of these trigger factors is they appear to operate in combination. So one alone wouldn't necessarily be sufficient to bring on a migraine, but multiple triggers stacking together might have that effect. In addition, these triggers seem to differ across patients, and there's uncertain timing. There's unknowns about whether a given exposure might induce a migraine within 2 hours or 2 days. So with prediction in mind, another stream of information might come from what's known as premonitory symptoms, which aren't necessarily modifiable factors, but they are symptoms that tend to increase in the day or two preceding migraine. So given this array of potentially relevant information and these unknowns about how these factors might actually operate, it's tough for an individual patient to begin to track their data, much less to analyze it in a meaningful way to learn how to predict or potentially prevent their migraines. So in light of all this, Lori saw the need for a mobile health solution to allow convenient, comprehensive tracking of these relevant factors, as well as conducting the analytics for personalized prediction and analysis of trigger associations. And there are actually a number of existing migraine apps in the App Store, but none of them, as far as we are aware, were developed specifically with the standards of clinical research data collection, and none of them actually present personalized migraine predictions. So specifically, this idea is a smartphone app paired with a wearable activity tracker to enable tracking of both self-reported survey data and passively collected data on activity, heart rate, and GPS location that would then enable personalized predictive analytics, as well as enabling richer clinical research with the goals of decreasing individual burden of migraine for patients using a system like this, and increasing clinical understanding of migraine for better care on the population level. So with this big vision in mind, we needed to break it down into a more manageable first step. And so that brings us to the STREAM study. So our current objectives for this study are, first, to develop an initial iOS version of the app, focusing on the data collection and clinical research components, as opposed to the patient-facing analytic component. We're going to use this app to conduct a 90-day observational study of several hundred persons with episodic migraine, in which they'll track their data using the app and an Apple Watch, thanks to the CDH. After the end of the study, we will provide them with basic analytic feedback to help them learn something about their patterns of headaches and triggers, but to not affect the observational nature of the study. And then we will use the resulting database to build predictive models and test a number of specific trigger hypotheses. So to accomplish this objective, we envision this sort of data flow diagram centered on a participant-facing iPhone app on their own iPhone. So some of the key components that we need here are a HIPAA-compliant server to store the data, since we'll be collecting PHI. The app itself will need to enable a consent and registration flow and collection of self-reported survey data and passively collected activity, heart rate, and GPS data. On the back end, we will also require a secure database to transmit this data from the server to a place where we can have it organized and immediately usable for monitoring study progress and future analyses. And finally, we also include our REDCap eligibility survey on this diagram. Our eligibility criteria for the study are somewhat involved, so we are administering that survey online so that only eligible persons will actually download and use the app. So zooming in on the app itself, this is the framework that we drew up initially with three main screens: a home screen presenting the surveys assigned for that day, a progress screen keeping tabs on the patient's adherence to the protocol, and an about screen allowing them to contact the research team or review the consent slides. And so to make this vision a reality, we started out working with Medable, which has a really fast and user-friendly interface for developing survey-based apps without any coding. We had a number of additional features we wanted to add on to that basic functionality, including the passive data collection, some unique branching between surveys, and some personalized notifications. So at that point, we got connected with Mike Hetal, who had experience in iOS development, and tasked him with building our list of extra features on top of the Medable platform. So at this point, I will turn it over to him to give some background on where he was coming from, and to tell the story of the development and approval process for the STREAM app and how that fits into his larger goals of digital health research.
Thanks, Catherine. So hi everyone, I'm Mike Hetal. So I've worked on actually 2 of these grant recipients. I was on the StrokeCoach project before working on the Stream project, and eventually what happened was they kind of merged. The code base actually that eventually ended up fueling Stream was the code base that we built for StrokeCoach early. Let's see here. So today, my real aim is to share my experiences in mHealth in building a mobile health application. Both of these projects are thankful recipients of the CDH Watch Grant, which was elemental in us achieving our objectives. Our road wasn't that smooth. We had our fair share of challenges. I think it's safe to say that everyone involved maybe underestimated those challenges and the challenges associated with bringing an mHealth application to life. But nonetheless, our road wasn't only paved with folly. We had some wins too, and we'd like to share some of those in the hopes that they'd be beneficial to some folks here. So my goal, or the process I'll go through, is I'm going to give you an under-the-hood look at Stream and StrokeCoach and the process from kind of point A to point B to develop those applications, and then pass it back to Catherine, who's going to show us the data pipeline and a little demo of the enrollment process. So my purpose actually coming to Stanford, I'm kind of a non-traditional undergraduate student. I might be 2 standard deviations away from the mean age of an undergraduate student. I had a previous career in web development and e-commerce and entrepreneurship and got, I guess, the digital health itch. I really saw great potential in benefiting our society by combining some of the tools that I had honed in my professional career with a knowledge of health and applications. And so coming to Stanford, one of my goals was really to accelerate digital health research at Stanford and beyond. So AI in health is a really interesting space. Traditional research is somewhat data averse in the sense that you spend a lot of time trying to limit your confounders and stratifying your data and kind of getting rid of data. Insight is really the bottleneck. Insight is kind of the scarcity in the traditional research paradigm. With digital research, you're data hungry. I mean, more data equals a better model. You're looking at automated insights. So insight is no longer a scarcity, but really what is the scarcity? Well, it's the data. So years ago, I kind of came up with this structure, this vision for what I felt was going to be the future of data collection in mobile health research. And what I identified personally was that the mobile platform was really the hub that all this kind of goes through. The mobile platform is this great sensor platform and siphon device that can really collect a ton of meaningful data that we can then associate with different medical conditions by storing it and sharing it and analyzing it. So today, I'd like to share my experience developing 2 mobile research applications over the last year, share the life cycle of a mobile health study and the development. I'd like to identify failures and missteps, obstacles, share some best practices, advice, and starter code, provide a little bit of guidance and input on other mobile health projects, and identify future research directions and opportunities. So this is a kind of broad overview of the differences between Stream and StrokeCoach, the other application that I worked on, and then the base layer that powers both of them, which I've started calling Cardinal Kit. So starting off, I'll let him take that picture and then I'll... All right. Starting off with Stream, these are some of the features. So we're looking at identifying triggers for migraines. We do collect PHI. It is HIPAA secure. We use the mHealth server here at Stanford, which is a phenomenal resource. We use Firebase. We're looking at daily and weekly surveys. We do collect heart rate data, step data, activity data, flights climbed, there's location tracking. We have custom conditional surveys and questions, and this was a CDH recipient of 350 watches. StrokeCoach, on the other hand, is almost the exact opposite in the mHealth space. We received a limited number of watches, and really the focus is more feasibility. So we were testing the feasibility of a digital therapist for stroke patients with hemiparesis. We were collecting no PHI. It was not HIPAA secure. We had daily and weekly assessments and exercises that were all anonymized. 3 levels of exercises ability, so patients were kind of stratified in clinic. And then during those exercises, we collected 100 hertz frequency accelerometer data coupled with gyroscope data from the Apple Watch. We connected with Firebase primarily for all of our data, and are able actually with this particular app to collect persistent, ubiquitous 50 hertz accelerometer data using the Apple Watch, which has all sorts of future implications in my opinion. So moving on to CardinalKit, which is fueling both of these platforms. These are kind of the key components of CardinalKit, and then the features that they enable on your right-hand side. So the mHealth server connection, this took a long time to build. The mHealth server, for all of you that don't know, is a resource here in Stanford that is HIPAA compliant. It's an incredible resource that accelerated our timeline. It's a very valuable research that, in my opinion, deserves more funding and more focus within the Stanford community to accelerate more digital health projects in the future. So with the mHealth server connection, we get consent and sign up, and it's pre-approved, so it accelerates you through the DRA process. With HealthKit, we deliver step count, heart rate, accelerometer data, activity data. With ResearchKit, we get some pre-configured tasks and exercises as well as some surveys. With WatchKit, we get heart rate, persistent accelerometer data at 50 hertz, and I think with the newer versions, you actually get heart rate variability. With the Firebase connection, we get scheduling and app settings and non-PHI data. So one distinction that's very important to be made between the mHealth server and the Firebase backend is that the mHealth server is actually one way. So there's no way to get for the app to actually retrieve information from the mHealth server. You post information there, all of your sensitive data, and then that stays in the Stanford kind of HIPAA compliant ecosystem. A few other features include notification, scheduling, location tracking, and then haptics. So we have some buzzes that take place on the watch depending on what your exercise is. So I'm going to run you through a quick kind of breakdown of StrokeCoach, which is what started this for me, and show how that kind of evolved into Stream and served as a base of Stream, and then address some other issues. So this is your main landing page. This would be where you would monitor your own activity and movement. This is where your exercises and your assessments are being scheduled on a daily basis. So every day you would open this up and see new exercises that were scheduled. This is a view of getting one of those exercises started. You have the ability to watch a video, instructional video, and then start the exercise. This is one of our collaborators who did most of these videos. Thank you, Hyung. And so with the Apple Watch, it's really important to kind of have a calibration that takes place at the beginning of every exercise. So we suggested the patients put their arm down by their side so we knew at least where it was starting from. So after the exercise is started, the watch is kind of buzzing and telling you you're in an exercise. This is your view on the app. And then when it's finished, you get this. And here's kind of the representation of you filling your activity ring as you finish all of your activities and exercises for the day. And then this is just some basic tracking, so showing you your weekly, monthly exercises and general movement. So that was one of the neat things that we added to this particular application is we actually quantified how much you were moving your arm throughout the day and then delivered you, some feedback based on that. And just to kind of refocus on what the focus of the study was, it was really assisting patients with hemiparesis. So, and then here's your exercise view again where you can see the level of completion. This was our timeline to present for the StrokeCoach project. So we started off in March of 2017, received our CDH grant of, that's a typo, we got 44 watches, submitted the IRB. We initially had this very ambitious thought that we would launch in August. Didn't quite happen. We got our IRB in August though, so that was great. Submitted our DRA in October and then got that in November and actually launched with our first patient in December of 2013. We were still kind of in a stabilization phase, so we had to do another release in January of 2018 and have been working through the study ever since then. So we're about to close on our last patient, I believe, Friday, which is pretty exciting. This was the initial plan. It went right out the window as soon as we got our hands dirty and started getting into iOS and watchOS app development, but it was a good starting point. But you can see there is a decent amount of complexity that goes into projects like this. So this is where we started from the design phase. Much credit, and I'll say this again and again, to Jason Zhang, who's here in the audience. He did a phenomenal job helping us through the design and aesthetic phase. So this was, I think, one of our first sketches where we were really determining what the functionality was, what the possibility was, what the opportunities were. And it's a process of kind of moving forward with what you think is possible and what would be neat, and then scaling it back when you determine what's feasible and what's not. So these are just some of our kind of design mock-ups, which were very early on. we made some very critical design decisions to focus on a very, very easy and easy to see set of user experiences for a population that might not be very accustomed to digital resources, might not be accustomed to some of the behaviors like swiping and things like this. So this was kind of our final design aesthetic, where we have our color scheme and general layout. Most of this translated into iOS. Not all of it did. There are some constraints just inherent in iOS and their kind of user experiences that that precluded us from a few of these elements. So this is kind of an overview. Again, huge thanks to Jason Zhang, who did a phenomenal job. He's an undergraduate student in CS here at Stanford and has surely a bright future. So into the kind of technical aspects of StrokeCoach, this is the actual diagram that we submitted for DRA approval. Pardon me if I'm going to bore you with some of these technical details. I won't run through everything here, but as you can see, a lot of very rich data is coming off of the watch, being given to the phone. The user ID is set anonymously in the clinic, and that's something that's really unique about StrokeCoach in the sense that we were collecting no PHI, so at no point in time in the application were we collecting any identifiers. And identifiers are very broad. I mean, what's actually considered HIPAA is a very, very, very broad kind of domain, and so we're not collecting any location, UDID data, no email data, no social security numbers, IP addresses, URLs, nothing is collected in the app. That's all done in the clinic in that HIPAA zone. So this data is passed to the phone, which then passes a lot of this kind of raw accelerometer data to the Firebase database, which then gets pushed to the mobilized server here at Stanford. An activity rating is then given back to the Firebase database, which pushes it back to the phone. So you can see just a listing of some of the very rich data that we were collecting here. This is a little bit more technical. I don't know how many developers we have in the audience. I hope I don't bore the non-developers here, but this is kind of an overview of some of the libraries and methods that we use in order to kind of construct this data flow. Some of the unique libraries we use were HealthKit, the Core Motion Recorder, Core Motion Manager. We use triggers to kind of light these things off in background processes. And then pushed all the data to the phone, batched it up into JSON files, and then pushed that data to the Firebase storage. Originally, we were going to use the mHealth server. This diagram is a little antiquated, and then to the Firebase real-time database. Now, the real-time database and data store are two kind of fundamentally different things. One stores files, the other stores kind of dynamic data. So onto the stream application. So the stream application, this is our landing page. When you first enter the application, you get an access code that we've given you through, I believe, REDCap. You go through the entire registration and enrollment process, which Catherine will be walking us through later. You get this thanks for registering, and then you're seeing your kind of main tab. So this is your, all of these are HealthKit surveys that get kind of spilled out. So, and that's the fundamental goal of Stream is we're basically giving the users daily and weekly surveys. This is your compliance adherence schedule, or not schedule, but view, and this is just kind of a settings page. So this process was fundamentally different because the user experience was very different. It wasn't quite so dynamic. A lot of the user experience was kind of created by ResearchKit and Apple, and so all we had to do was kind of modify that and use it for our purposes. But the timeline was different because we had a couple missteps. So the project officially started really when we got the CDH grant, and we began development with Medable. Medable is a great group of people. They have a great platform, and they're doing some really, really interesting things. We started off with that platform, but found that it just didn't quite suit our needs. I think Medable is really great, and you can probably get a mobile health study up off the ground in less than a month if you stay within the bounds of what they deliver with their core experience. That wasn't quite us, and so we tried really hard to work with their platform, and it didn't really work out for our needs. At the end of the day as well, when we got to the DRA process, we ran into a snag because what was new to us was that if you have a BAA, so a business associate, I think addendum with Stanford, that doesn't confer a DRA, so a data risk assessment. So these are two different authorization paths that are critical to be able to operate inside of Stanford as a third-party software provider that's dealing with sensitive data. This is a nuance that I think escapes a lot of teams that are starting mobile health studies, so hopefully with this information I can help you all avoid a few obstacles. So that was kind of development 1 you can see on the left, and then development 2 was once we inserted the CardinalKit platform underneath. We got almost immediate DRA approval and have been working on the app ever since, and are currently awaiting review in the App Store and looking to start the support phase. So the I'm sorry, this is mislabeled. Nonetheless, the stream kind of design and evolution was fundamentally different than that of StrokeCoach, mainly because the interactions were a little less nuanced. We were a little less dependent upon the user for these kind of specific kind of exercises and interactions. This is a slide that shows the evolution of our logos. This was the slide that Catherine showed earlier, so this is our just very basic layout, which evolved into some more wonderful designs that were delivered again by Jason Zhang. And this was our final product. So this is the final user interface that we decided upon. So, here. So back to the Dataflow. I'm not going to focus too much on this because we've already seen this, but you have a lot of data that's being self-reported on the phone and then sent to the mHealth server and then processed and analyzed inside of a HIPAA-secure Stanford ecosystem. So I want to touch a little bit about development costs and what it takes to actually create a mobile health app. So this was a study that was done on 2,400 mobile health apps and delivered in 2017. So now keep in mind that this is a different group than us, right? These individuals are needing to market their app. They're needing to go through additional kind of rigors and spend additional money on business-focused goals. But nonetheless, I feel like the cost of building the app is at least something to use as a benchmark when you're trying to determine how much time it's really going to take for you to build your mobile application and how much money it's really going to take for you to build your mobile application. We didn't spend near this, but had I billed for all of my time, I don't know if it would have come close. So this is from the same study, and this kind of shows you that the average development time is 15 months. Funnily, I think if you look from March of 2017 to now, the stream development process has taken about 15 months. So we're right in the middle there. StrokeCoach might have been a different case, but StrokeCoach also is much less scalable than Stream is and isn't dealing with any PHI data. So here is CardinalKit. This is the back end that powers both Stream and StrokeCoach. This is the GitHub kind of stat view. So this is how much development activity has been taking place over time. So you can see that there's a big peak when Stream gets added on, another big peak before we launch StrokeCoach in December, and then some continuous development ever since. This is a group of the contributors, so we've had a total of 7 contributors that have worked on CardinalKit. We use a group of undergraduates that were very, very helpful early on, kind of identifying some of the unique Watch OS difficulties. There's definitely a lot of struggle trying to open up Watch OS and get it to do what we wanted it to do. We also engaged 2 external freelancers who were critical in helping us kind of get through snags that were beyond my own development experience. So I want to talk now about some critical obstacles and challenges that almost every mHealth study inside of the Stanford ecosystem is going to face. And the big, bold, looming challenge is privacy, HIPAA, and DRA. Anything that you've known about app development in the past, you can kind of throw out the window because none of your tools, well, some of them might still be applicable, but once you start operating in the privacy sphere, a lot of those tools kind of go away. Other kind of obstacles and challenges include the development team, time and cost. We had several people kind of come and go and work for a little bit and maybe come back and work a little bit later. It's not a matter of whether there are bugs, it's just how many bugs there are. So, QA testing becomes a very big issue, and then ongoing support is also a challenge that needs to be faced. So let's talk a little bit about the data risk assessment, because this is probably one item that I think most mHealth teams at Stanford get maybe hooked up on. This is a combined effort of the Stanford Privacy Office and University IT to mitigate risks associated with sensitive data. One thing to note is that the teams that are working on this, these are kind of unsung heroes in the sense that they're successful if nothing happens. So they don't necessarily have, a metric they can say, well, I performed really well and, high five. They do well when nothing happens. And that's a very interesting, I think, paradigm just to be aware of when we're approaching these folks. So key DRA challenges include insidious HIPAA identifiers. So any timestamp whatsoever is really considered PHI. An email address is considered PHI. A UDID is considered PHI. The definition of PHI, especially if you're taking a conservative approach to security, is very, very broad. There's a somewhat unclear timeline for completion. Partners with the BAA still require a DRA, and that was a big surprise for us. And there's limited communication between the different centers within Stanford. So the folks at the DRA don't have a whole lot of communication with the folks in the BAA group. Outside vendors, and I ran into this with a different project just recently, will often require kind of external validation in certification that can be very costly and very time consuming. So ISO certification is sometimes required. External audits that can run upwards of $100,000 might be required for an external third-party software provider that's not already approved inside the Stanford ecosystem. So these are just things to keep in mind. I think there are a lot of really interesting startups out there that really want to collaborate with Stanford researchers. If they're collecting PHI, it's going to be an uphill battle to get their app approved, and it's going to be a very, very long process. And one thing to note is that the lead on a DRA is often a lawyer. So digging a little bit deeper into the DRA and what they do, there's a lot of focus on data classification. So we have low and moderate and high risk data, and PHI actually has its own class of high risk data classification inside of the Privacy Office. So there's a list of approved services. I'm sure many people have seen this before. This gives you an idea of what is pre-approved and kind of ready to go for DRA approval. When it comes to storing your data, really Microsoft Azure and the Google Cloud Platform are the only cloud infrastructure pieces that are pre-approved. But even if you use these pieces, you still need to have your pipeline pre-approved, or not pre-approved, but approved through a DRA process, and that can still take some additional time. So some of the suggestions that I have for anybody that's starting an mHealth study would be, number one, start the process at this link before you do anything. This is the pre-screening form for the DRA folks. And you need to integrate their feedback and their restrictions into your design process. This is going to be a critical perspective and view in your design process, and if you don't integrate that very early, you're going to run into snags later on. Use the mHealth server. I mean, the mHealth server saved us a ton of time. It's pre-approved, it's internal in Stanford, it will accelerate your DRA, and it's a really wonderful resource. Garrick and his team do a phenomenal job of keeping the server up, keeping the server secure, and making sure, like the Privacy Office wants, that nothing happens. Self-plug, use CardinalKit. This is a great starting point for PHI and non-PHI, depending on what your app might be. Err on the assumption that all of your data is PHI. That might help you later on. If you build for PHI and then have to scale it back later, it's a lot easier than building an entire infrastructure and then trying to shift that to a PHI HIPAA compliant infrastructure, and I would recommend against depending on third parties to get these approvals. I mean, there's a limited incentive for a small team on a startup to spend $100,000 plus that it might take to get their certifications and get approved, through the Privacy Office. So now I want to identify a few mistakes and kind of shoots. Has anybody played the game Chutes and Ladders when they were younger? Yeah. Okay. I think that game might be a little antiquated. I'm going to grab this water real quick. So I want to identify just a few shoots, a few mistakes that we made through both projects that I think can be used to accelerate your own projects. Number one, I think we underestimated the amount of time that it would take. I would recommend seek more funding. I mean, if we had more funding, both these projects would have gone smoother. I mean, I think that probably applies for most problems, but nonetheless, it was a mistake that we made. I think depending on unpaid student developers was a potential issue. I think that research credit becomes a low priority for a lot of students, so I think that actually paying the students that are working on your project makes a lot of sense. We underestimated development time and issues. We drastically underestimated the watchOS challenges. So the watchOS has a fundamentally different kind of processing time awarding scheme than the phone, and that definitely threw us for a loop. Our patient inclusion criteria for StrokeCoach was perhaps a little too precise. Recruitment was challenging. We started with the idea that we'd get maybe 44 people. We ended up with 7. I think if we were to do that again, we might focus on a broader group. We chose a vendor based on assumptions without first making sure that they were kind of approved to operate inside of the Stanford ecosystem. We hired a bad fit for a first freelancer. Not that this person was not incredibly talented, actually they were a little too talented for our project. So, there's a very big difference between creating an application for an mHealth study and creating a full-fledged commercial application. There's a very big difference in cost, there's a very big difference in quality of code and iteration, and so we hired somebody that might have been a better fit for the latter. And then the scope of PHI, it was a big surprise to us that any timestamp was considered PHI by the Privacy Office. So a few technical snags and challenges. A lot of this will just sound like jargon to some of you. Some of you might actually understand what I'm talking about, and some of you have probably shared some of these challenges. So Grand Central dispatches mysterious ways, the mysterious ways of the background queues in watchOS, watchOS code execution limitations. So the Apple software update dependencies were really challenging. So if all of your software stack was not up to date with the most recent software, you'd get these very strange ambiguous failures where you couldn't compile your code and you wouldn't really know why. There were no pre-existing use cases or implementations for persistent accelerometer data, at least none that I could find, maybe some proprietary ones out there, but no public code was available. So there was really no starting point when trying to embark on this. More ambiguity inside of iOS development. Threading and async processing is somewhat ambiguous, and somewhat unclear. And then WC session latency and ambiguity was definitely a challenge. So key ladders, though, or accelerators include using the mHealth server. I mean, this was a critical accelerator for us. If we would have had to go outside of Stanford and try and use the Google Cloud Storage Service or some other HIPAA-compliant server, it would have probably added a year to our timeline. So this was a big accelerator. Finding a key developer that had a sufficient commitment. Utilizing freelancers for advanced issues, maybe not for everything, but for the snags that are beyond whatever your student developer's abilities might be. Repurposing the code, so bringing Cardinal Kit from Stream from StrokeCoach to Stream was a big accelerator for Stream. And starting the DRA conversation immediately. So one of the first things that we did in our project, I think at the guidance of Matt Smuck, who's going to talk later, was to engage with the Privacy Office immediately. Just grit, which can be really important when it comes to developing, especially if you're doing a lot of development on your own. Keeping all the iOS software updated. This actually, it seems like an obvious thing, but it's somewhat difficult to do. So once we started doing this, the code flow was a little better. And then just depending on Stack Overflow to address any coding challenges that we were unaware of. So some early observations from StrokeCoach. Some patients were really surprisingly excited and motivated to participate even after. So patients have actually been asking for more exercises after the study has ended. We learned that WMFT is maybe not the best assessment mechanism. Recruitment was a challenge. We did learn that the Apple Watch is as valid as an average IMU, which was a big surprise to us. And another interesting observation, which is very early, is something highlighted here. So Mazen Alborno in the neuromuscular biomechanics lab was able to do this with some of the watch data, which is pretty neat. This is all just data coming off of the watch with the gyroscope and accelerometers. So to touch a little bit on one of the key features of CardinalKit, so the persistent accelerometer data, in my opinion, is very meaningful to research in a number of different areas. I think the characteristics, so we're looking at about 30 megabytes of data per day, minimal battery impact, XYZ coordinates, but no, well not coordinates, but XYZ acceleration, but no gyro. It's collected whenever the watch is worn, so my watch right now is collecting that data, and it's aligned with steps, heart rate, activity, and location. So possible future research areas for this particular data stream include sleep, fatigue, gait, EDSS monitoring, disability monitoring, fall detection, gross activity classification monitoring, and functional testing. So with that, I'm going to pass it back to Catherine, who's going to show us a little bit about the enrollment flow for Stream and then the data pipeline. So there you go, Catherine.
Thanks, Mike. So Mike has covered a lot of the key steps and challenges and successes of the app development process. At this point, I'll bring it back to the current functionality of the Stream app and then touch on the data pipeline on the other end of the mHealth server. So just quickly here, we will show the enrollment flow for how someone starts using in the Stream study. So our eligibility survey, as we alluded to, is administered on REDCap. For eligible persons, they are given an access code so that they can then download the app and enter that code to get access. They go through a consent process that's made possible by ResearchKit functionalities. We were able to include a number of unique slides in here, as well as a consent quiz to verify their comprehension, and then a consent review for the main study, as well as a special HIPAA authorization consent. And then they'll make a signature and move on to registration for the study. At this point, they must verify their email. This is required within the mHealth server, so they get automatically sent an email, they'll click on the link, and then be able to proceed to the next step within the app, in which they will just sign in with their email and pre-populated password. And they'll do this every time upon entering the app and go to the main screens that were shown earlier. So just wanted to demonstrate that briefly. Then on the other end of the data flow, so we have the data coming in from the app to the mHealth server. This is back to our original data flow diagram. And so we discussed the challenges of developing the app itself, getting that data coming through in the first place. Just touching briefly on the pipeline to bring all the different types of data from the mHealth server to a secure database for study monitoring and future analyses. So the mHealth server has a pretty minimalist setup. The available commands to get the data are authentication, getting a list of available files, and then downloading a single file. So I started sifting through the data one JSON file at a time, and then I took an excellent class on R for data science and learned all these R packages for HTTP requests and JSON manipulation and SQL databases. So I decided to start developing an R package to make it easy to download this data in bulk and organize it, and even visualize study progress. So the key functions of this come on. Where shall I go?
One lesson that we've learned through this demo is Prezi is just not what it used to be.
Well, I don't know. I'm not sure at this point where that particular slide went, but I can just describe the key functions of this R package that I'm building. Initially, the idea is to take a simple Excel data dictionary, take that in, create a SQL-like database stored on box sync with empty table shells. Then the next step is to download data recurrently from the mHealth server that'll come in JSON format to a Stanford encrypted machine on the Stanford network. The next step is to classify and organize that data according to its type, whether surveys or consent or activity or heart rate, and convert that from JSON format into a table format, append that to the tables, and then additionally to make some simple visualizations of study progress, like enrollment progress and percentage of persons taking the screening survey who are deemed eligible, and percentage of those who actually enroll in the study. Also, with the STREAM study and a number of other mobile health studies, we're asking intensive data collection over an extended period of time, where we need to have real-time monitoring of who's participating, who's falling behind on the protocol, so we can follow up with them. So additionally, this package will enable easy tracking of participants completing their surveys and things like that. And so a takeaway here is that once you've put in all this time and money and energy into developing the app itself, don't forget that it takes time and thought to build the pipeline to bring the data from, say, JSON format on the mHealth server or whatever server is appropriate to your study into the form of neat tables and graphs for your study management and later analyses. And so the goal is that after we finish building out this package and testing it and refining it through our study, we can make something like this available for other researchers using the mHealth server for their mobile health study. So now I will turn it back to Mike to wrap us up.
Okay. Thanks, Catherine. Sorry, your slides went away. Okay, so the current status of STREAM, we've gotten the IRB, DRA, app development, beta app. We've been through Apple test flight, done a lot of QA testing and bug fixes, and done an internal pilot. The next 2 weeks, we should be launching an outside pilot once we get App Store approval, and should be launching our study within the next 2 months. Current status of StrokeCoach, we got our IRB, went through the entire same process, launched our internal pilot, our outside pilot, a feasibility study, N of 7, and we're closing that study this week and should be doing the data analysis and write-up, and actually are talking this afternoon about next steps. So a few items I'd like to address is just suggestions on how we might, as a Stanford community, further accelerate mHealth. So the way that I actually got into mHealth, at least here at Stanford, was through a class called CS96SI, iOS and Mobile Health, through the Shift group. It was a phenomenal class which actually laid the groundwork for Reclaim, which then became StrokeCoach, and subsequently Cardinal Kit. So this was really great for me and a lot of other students who have gone on to actually work on other mobile health projects here at Stanford. So I think that we need something like this in the curriculum. I think more funding, support, and promotion of the mHealth server, because that benefits everyone. There's less DRA cost. It reduces your study launch timeline from 1 year to 2 months. And a formal adoption and community support of either Cardinal Kit or some other centralized starting point for mHealth studies. So I don't think that there's any reason why we can't have a central kind of trunk that we can branch out here in Stanford. And I think that saves you up to $200,000 in 15 months per study of cost. So in closing, we really hope that we've helped you identify some possible obstacles and best practices that help you design and execute your own mHealth study. We hope hearing about our experiences have been fruitful, and please reach out if you have any questions or need advice or need help with your own mHealth studies. And we have a long list of people to thank. Some of them are here in the audience. I really appreciate everyone's contributions. I mean, none of this was done alone. I'm not going to go through reading this entire list, but these are just some of the people that made very key and critical contributions to getting us all to where we are today. So with that, I appreciate your time and attention. I don't know if we have too much time for questions, maybe 1 or 2 at most. But yeah, thank you.
Thank you.
Yeah.
So yeah, let's go ahead and open up for a few questions before, Matt, if you could come and start setting up the slides. Oh, we got one over here. Let me pass out this.
Are there any projects related to adding remote wireless sensors from other parts of the body that go further deep, watch, or might be more relevant?
I'm sure there are. I don't know of any right off the top of my mind, but absolutely. I mean, I think it's a very, very interesting and hot space right now, and I think people are doing a lot with wearables all over the landscape.
Thank you. Great presentation. Question, I know your study's kind of very small right now, but as you expand it, what are your plans to have more diversity in your data set in terms of gender, race, age?
It was really interesting to focus on because with an eye
Do you guys ever consider using RedCap for all the data? And am I speaking with the RT people? They're now opening that up as another option.
I don't have any experience with RedCap.
At the time we started development, I don't think that they had the patient-facing mobile app available. But going forward, that seems like another great option.
Yeah, even without the patient-facing mobile app, you could still use the RedCap backend as a study data backend, and you could use that, I guess, instead of mHealth, but you probably still want the Firebase.
Sorry, I'm Catherine. I work with Mike on StrokeCoach. So we used actually RedCap for all the clinical information for the StrokeCoach. And we used it also for patient questionnaire of like their appreciation of the device. So we did use RedCap.
And so for folks that aren't as technical, you can find a lot of this information on our website. We've held a workshop on privacy and security. We had the Chief Privacy Officer talk about the complexities of the DRA, which stands for Data Risk Assessment, the BAAs when you're working with outside companies, things like that. It gets quite complex, so we tried to roadmap out what that looks like and get the link outs to the appropriate teams, because I can't... I'm impressed with how much your team has completed with such limited resources, because it's such an immense effort to launch one of these projects, and it's great to see all the different pieces of Stanford come together, student communities, faculty, and researchers. Yeah.
Do you have a goal for migraine prediction accuracy? And if you do, how many data labels, meaning how many migraines per individual do you think you will need to collect to achieve that accuracy?
Yeah, so only been a couple of previously published studies.
Great. Well, we can hold the rest of the questions for at the end. I'd like to introduce our second speaker here, Dr. Matthew Smuck. Thanks very much.
Okay, thank you. Very happy to be here, and just in transition, I would like to second a lot of things that were said in the last presentation. I'm not going to present on it today, but I've spent the last 2.5 years developing a research app study for self-management of low back pain. And I really wish CardinalKit was available when we started that 2.5 years ago. And I'm just now at the point where we're getting the IRB approval, and we're going to submit the app to Apple for review and hopefully be able to launch the study within the next couple of months. And really, it does a lot of this, has a lot of similar functionality to what you just heard described, which those two studies were developed in the course of 8 months, and I think 15 months the apps were completed, which is incredible given that that's at the average duration of app development out in the commercial sector when you don't even have all of the challenges for app build and design. And I'll just say that I did meet with Mike early over the StrokeCoach development and voiced some skepticism about the ability to accomplish the goals of the app development and the time frame that was set out. And Mike's grit and the team's grit carried that out and accomplished things much faster than I thought would happen. So the ability to do that, I think, is proof in the pudding. And this Cardinal Kit platform, I think, is going to really accelerate digital health research at Stanford. So I'm super excited about it. Okay, so with that said, I'm going to talk about physical performance monitoring. And that's really a passion of mine, and it's sort of a new area of research that we're opening up right now. And it's going to build a new, and it is a digital health tool. These physical performance monitoring relies on digital health techniques and tools in order to provide the assessment of a person that we look for in physical performance monitoring. And you probably have no idea what I'm talking about with physical performance monitoring. So I'm going to first start out about the clinical motivation for that, kind of what I mean about physical performance monitoring, what the clinical motivation is, and then how we've used digital health tools in order to solve those clinical problems that drove this science in the first place. Before I get into that, I want to thank the very talented people that I get to work with in the research lab, and also some key collaborations at Stanford that have really helped accelerate the science, including Scott Delp through the Mobilize Center, and Bill Haskell, who ran the Stanford Prevention Center when I arrived at Stanford, and was the first person I sought a meeting with, and who was very generous with his time and resources in helping me get started. Nigam Shah and his lab, and the really incredible bioinformatics approach they're able to bring to this data. All right, so if I could summarize my talk in one word, that word is function. All right, and why am I talking about function? Well, I'm going to explain, but you have to understand that function means different things to different people. If I talk to a group of computer scientists and say the word function, that has specific connotations for them that are different than they are for me. So I want you to understand two key bits of information that will describe for you what I mean when I talk about the word function. And those are, first, that I'm a physiatrist. I'm a physical medicine and rehabilitation physician. And some of you probably never even heard of that subspecialty in medicine, and others of you probably have. But it's one of the smaller subspecialties in medicine. The subspecialty developed in the 1940s in the World War II era, when advances from antibiotics and anesthesia in order to allow for certain types of surgeries made it such that wounded warriors started to survive. Prior to World War II, very few wounded warriors would survive. If you needed an amputation, you might survive it, but many didn't. If you had a bullet wound, odds are you were going to die as a result of septicemia or some other complication from that wound. Come World War II, medical science had advanced to the point that they could save those folks from their injuries. But they were left with debilitating injuries that nobody knew what to do with. And so the field of physical medicine and rehabilitation grew out of the need to help people who were injured in war, who wanted to return to their communities and to their lives and maintain as much independence as possible. And so a physical medicine and rehab doctor thinks about the human in terms of their function. How can we optimize a person's function for their condition? And function is what we own. Orthopedic surgeons, they own the bones. Neurologists own the brain and the nerves. Dermatologists own the skin. Physiatrists, we own function. So we think about human function as the core of how we approach disease and the human condition. And so really, when I talk about function, I'm talking about human function. The International Classification of Function, which is the second item here, is a group under the WHO. And this group has created, hundreds of pages describing human function and built the whole rubric around human function and what it means. And they describe human function in two main components, or describe two main components of human function. And those components are capacity and performance. And this brings me to what is physical performance. So capacity is described by the ICF as a person's ability to do something in a controlled environment. So how much can you bench press, or how fast can you run, or how quickly can you do the stair climb test or a sit-stand test. Many different things we use in medical research, especially in the laboratory, test a person's physical capacity, okay? Physical performance, on the other hand, is how you do in your normal life. What your physical abilities and habits are sort of like in your routine and normal life. And those two things are separate constructs, and you can just think about a sporting example to illustrate that. So the fastest sprinter in the NFL isn't the best running back or receiver, and the lineman who can bench press the most isn't the best performing lineman typically. So a person's capacity doesn't predict how they perform on the field in sporting competition, and it doesn't do so for us either in our regular lives. So you have to think about those two things separately. The other interesting piece of this is that when patients come into my clinic, and I spend about 40% of my time in the clinic treating spine disease, that's my focus. When patients come to me in the clinic, their issues are that they hurt and that they have deficits in their physical performance. They don't tell me, you know, I can't bench press, now I'm bench pressing 10 pounds less than I was the week before. No, they say stuff like, you know, I can't get on the floor and play with my kid like I used to, and if I do X, Y, or Z, I suffer as a result. And so it's physical performance that is really the main measure of what's aggravating or meaningful to a person when they have an orthopedic problem. So physical performance monitoring is about a new way of looking at people's ways of behaving in their regular lives. And I touched on this, you know, just briefly a moment ago. When we think about musculoskeletal diseases in general, not just spine research and spine disease, which is my focus, but when we think about musculoskeletal problems in general, we measure two types of outcomes, two things that matter when we try to, you know, determine the severity of a problem and when we want to track a person's response to treatment. We look at pain, because that's a very important aspect of this, and pain by its medical definition is a subjective thing. So you can never purely quantify objectively pain because the subjective experience of pain is built into it. And then we look at function. And typically we determine function, and by typically I mean 99.9% of the time in research, in the orthopedic space, we measure function by self-report. We have disease-specific and validated patient-reported outcome measures where people report on their function. On a scale of 1 to 5, where 1 is no difficulty and 5 is you can't do it, how much difficulty do you have in getting dressed, climbing stairs, you know, on and on. We ask these types of questions, and we use those functional outcomes to determine the functional impact of disease and improvement in function in response to disease. But there's a problem with that approach, and it's what I think is the biggest problem in orthopedics research. It's that all of that science is purely subjective. And subjective science is important. It's important for me to know what my patient thinks about their condition and how they feel about their condition. But if I want to iterate improvements in the science over time, like has happened in cardiac research and cancer research, you have to have a very precise and objective measurement that's meaningful to the disease process. And we don't have that because we rely on these subjective outcomes. Not only does it cause issues with the precision of our science, I came to realize it also creates problems in the clinic where it creates a barrier between the patient and the clinician having a meaningful conversation about choices that the patient has to make about how they're going to approach the treatment or the management of their disease. So I want to go through a couple of quick examples to illustrate these two problems, the imprecision of outcomes measurement and the doctor-patient relationship issue. So if you consider two patients that come into their primary care physician's clinic on the same day, and one of them has low back pain and one of them has chest pain. We'll just kind of hypothetically go through the scenario real quick. So the back pain patient comes into the clinic. The primary care physician says to the patient, well, how bad is your pain? Can you rank it for me on a scale of 0 to 10? And they do. And they ask them questions about, how long has it been bothering you? What kind of things have you tried for it? Did you take some aspirin? Did you try Tylenol, any over-the-counter anti-inflammatories? Have you been to a chiropractor? Have you tried physical therapy? Getting kind of a laundry list of things that the person's tried. And at the end of the encounter, they may get an x-ray or not. That's meaningless. What they say to the patient is, okay, Mrs. Jones, my diagnosis is that you have low back pain. Okay, that's what Mrs. Jones says. She had low back pain. It's a symptom. It's not really a disease. And she says, here are the things that you've tried, and here are the other options that are available to you. How do you feel about these different options, and what do you think you want to try next? And through a shared decision-making process, they come up with an idea about what to do, okay? So that's what happens with low back pain. Consider the chest pain example. A patient with chest pain comes into the primary physician's clinic, and imagine the same process happening. Mrs. Jones, so you have chest pain. How long has it been bothering you? Can you rank it for me on a scale of 0 to 10? What have you tried for your chest pain? Have you tried aspirin? Have you tried exercising more? What else have you done? Well, we have these other options for you. We could get an EKG, or we could maybe do a cardiac stent or a CABG, a bypass, big surgery. How do you feel about those treatments? And what would you like to do next? That's not at all how it happens, right? What happens with the chest pain patient is they get a meaningful history, and then they say, okay, we're going to do an EKG, and if the EKG points toward a problem with the myocardium, you do some laboratory testings that help determine whether or not that is a meaningful objective finding on the EKG, and then that objective laboratory testing tells you, do you need to take them to the cath lab in order to look at another objective marker that tells you specifically what's going on with the blood vessels, that then tells you what you do to that blood vessel, whether you put in a stent or you operate or whatnot. And so all of those decisions are data-driven and very precise. And not only that, you can then change your decision points and say, okay, if we take this marker and change our decision 10% in one direction or the other, how does that affect outcomes for people? Because then you can also measure the outcomes, because percentage of blood flow through an artery, ejection fraction of the heart, and death are all very objective and quantifiable measurements that are meaningful outcomes. And so the science has a lot of capabilities that we don't have in the orthopedic space. Now, with the doctor-patient relationship, I want to play this video to reveal how I think the current state of the art in orthopedics research limits our ability to communicate with people. And I think this is set up to play. We'll see. But I just found this video online, and it's very interesting to me because it illustrates the point I want to make.
Hey everyone, I thought I would make this video because it has taken me a really long time to finally come to the conclusion that I wanted to have surgery for my herniated disc. And I feel like if I had really had, support or people around sharing their experience, it probably would have assisted me in making my decision more quickly, not having to wait so long and suffer as long as I have. So I thought, hey, maybe if this helps someone, great.
So I have no idea who this woman is, but she could very well be my patient, right? I'm going to assume that she saw good doctors who gave her good advice, and already admitted that this same confusion happens frequently in my clinic, and I'll go through a hypothetical scenario to describe why. So what you don't know, before I go into the hypothetical, what you don't know that I know is that a herniated lumbar disc, like she has, is the one thing that we know the most about in all of spine medicine, okay? We know about the pathophysiology of it, we know the natural history, we know the response rate to treatments, we know lots about all the different treatment options. We have a very good algorithm of care that's better, it's based in more science than really anything else we do in spine care. But yet, somehow, she's confused about what to do, and she's saying, I wish I knew more, I wish I knew what my decision about this would mean for me, and I think I would have decided earlier to have surgery if I knew more, but I've suffered for a long time, and now I'm moving ahead with that. So how does she get in that situation? Well, here's how. Remember, we measure pain and we measure function, and that's what tells us about her science. So she's in my clinic, and I'm just going to call her Jane. Jane's my clinic, and she says, you know, Dr. Smuck, I'm not getting any better with all the things that you and I decided to do through our shared decision-making process before. So what do you think I should do next? And I say, well, Jane, I think you should have surgery. She says, well, I'm trying to avoid surgery. I've heard spine surgery is bad. You know, all this stuff in the media about how you shouldn't have spine surgery, and I'm trying to avoid that. Why would you recommend I should have surgery? And I say, well, we've researched this, and for people in your situation, if they have surgery at this point in time, 90% of the time it's successful. So for most patients, the conversation ends there, to be honest. But she's inquisitive, and she says, okay, Dr. Smuck, that sounds great. What do you mean by success? 90% sounds good, but what does success mean? And this is where the conversation falls apart. I say, well, success means that you improve in your pain and you improve in your function. And by function, I mean what you can do, you know, day to day. These are the things that we care about in our outcomes. And she says, okay, so that means there's a 90% chance that my pain's going to go back to normal and my function's going to go back to normal? And I say, whoa, slow down. No, that's not at all what I'm saying. The way we determine success is we've developed this threshold for success that we call the minimum clinically important difference. And so for your pain, for instance, we've determined through lots of research that an improvement in 2 points on that 10-point scale of pain is the minimum clinically important difference. So that's the threshold of success. And she says, Jane says, okay, Dr. Smuck, so you're telling me that my pain, which is at an 8 right now, goes down to a 6, that's success. And I say, yes, that's success. And she rolls her eyes and she says, that's terrible. I don't want to have surgery in order to have my pain go from an 8 to a 6. Why would I do that? Why are you calling that success? So, okay, I trust you, Dr. Smuck. You seem like you care about what's going on here. So maybe this function side of thing will convince me that I should have surgery. And I say, okay, well, let's talk about that. So we have the same thing here. We have a minimum clinically important difference. And so if your function improves beyond that threshold, then we call that success. And she's like, okay, well, describe that to me. And I say, well, if you remember when you first came to clinic, we gave you some questionnaires to fill out. And there was one questionnaire that you filled out that asked you about, you know, how difficult it was for you to dress, to go to the bathroom, to have sex. And she says, yeah, that was kind of weird. I remember that questionnaire. It didn't really mean much to me because none of those questions really focused on what I'm having problems with, but yeah, I kind of remember that. And I said, okay, Jane, well, that questionnaire is called the Oswestry Disability Index, and it's been highly validated for low back pain research. And it tries to assess a person's function. And if your score on that test improves by 15%, then we call that a success in your functional improvement. And she's completely lost in the conversation because that has nothing to do with what she is trying to determine, which is how can she know what surgery is going to mean for her. And all of my knowledge about the science is based on pain scores and the Oswestry Disability Index and stuff. It means nothing at all to Jane. And fortunately, there's an exception that really proves the rule here, and that is with professional athletes. So you may or may not know, Stanford Orthopedics takes care of the 49ers and the Warriors and different professional teams around the Bay. And when one of them herniates a disc, they often wind up seeing me. And if that happens, and we get to that exact same point where I'm recommending to this professional NFL player that they need to have a discectomy, a surgery for a herniated disc, the same conversation that I have with Jane is different. It goes like this. The player says, okay, why would you recommend surgery? I say, well, at this point in time, if you have surgery, there's a 74% chance of success. Not 90, like I told Jane. I say 74% chance of success. And he says, okay, what does success mean? And I say, success means that once you recover from your surgery, which takes about 6 weeks, you'll return to play. And in the next season of play, your on-field performance is going to be exactly like it was before you injured your back. All of your on-field statistics will return to the same level as they were before you had your back injury. And that's exactly what the player wants to know, right? Why should I do surgery? What's the odds that I'm going to return and return at the same level of play? And the reason that I can give them a more precise answer is because these people have their physical performance measured week to week throughout their careers. And we can take a group of 100 NFL players that have had discectomy surgeries and say, what percentage of them go back to their same on-field performance as before? So through all of this, I hope I've at least illustrated that physical performance matters, and being able to measure physical performance regularly has strong implications for orthopedics research, and not only that, just our ability to interact with patients and for patients to make insightful and meaningful decisions about their care. So the solution now is either to find a way to get all people playing in the NFL, or to find ways to measure the physical performance of everybody in their normal lives. And that's what I want to talk about next. So, clearly there's a communication problem here I want to solve, and it starts with what we measure. And that brings me to this, which is in 2007, I got my first iPhone. And prior to that, I was frustrated by the things we just talked about. I hadn't really formalized all the, it wasn't as clear to me as it is right now, but I had these frustrations as an early career researcher. I was trying to figure out how are we going to be able to better measure what we're doing, because it just, the precision of our science is so bad. And then I got an iPhone, and I thought, okay, this is a game changer. Now we have a way of measuring function or physical performance routinely for normal people, because this has sensors in it that are used to measure physical activity. And physical activity research is a very robust research field in the early 2000s. By that point, I had decades of good work using the sensors that were in a regular iPhone. Not only that, there's other things that the phone's doing that can measure what's happening in a person's life. So it seemed to me like it might be a game changer. And at that time, I moved from University of Michigan, where I started my career, to Stanford to really focus on this problem. And so, soon after that, Fitbit came along, activity trackers became really popularized, and it seemed like, well, that would be a simple solution to measuring physical performance of people in the world and during their regular lives, and so problem solved. But it didn't work out that easily, because the first thing we did was to look at a literature search in the orthopedic space. And back in 2008, there were less than 10 published scientific studies of any orthopedic or musculoskeletal condition that actually objectively measured a person's physical activity. All of the existing research, besides those 8 studies that we found at the time, asked people about their function as self-report. So less than 10 studies that actually measured it. And it's surprising because, the functional piece, like I told you, is very important. But not only that, inactivity, physical inactivity, is both a cause and a consequence of most musculoskeletal problems. So it's a mechanism of the disease as much as it is a consequence of the disease. So knowing about it in an objective fashion seemed very important. Not only that, a lot of the outcomes from the objective studies showed counterintuitive results. That being, what's shown here, hip and knee arthroplasty are considered highly successful orthopedic surgeries, and patients report on these self-reported measurements robust improvements in their function. But when you measured their steps per day, there was really no change before and after surgery. Why is that? What's going on there? So we set about looking into this more. And one thing we did is we said, well, let's look more carefully and maybe look at more than just step counts. And so we used kind of the existing techniques in the physical activity research world, which is to measure the intensity of activity, not just quantity like steps per day, but actual intensity of activity, where the focus is on moderate and vigorous physical activity. And in 2008, guidelines were established around how much moderate and vigorous physical activity an adult should pursue within a normal time frame, which is based on a weekly basis. And it turns out we're supposed to get 150 minutes of moderate and vigorous physical activity based on the 2008 guidelines. And so when we use that threshold, we actually see pretty significant impact of certain diseases. And this is a study of patients with lumbar spinal stenosis, where only 4% of people with that disease process meet those guidelines. And when you compare that to other older adults, it's pretty significant. Adults in the U.S. in general, only about 20 to 25% of U.S. adults meet the guidelines. Older adults, it's somewhere between 10 to 15%. If you look at the knee osteoarthritis population, it's right around 10% that meet these guidelines. But then lumbar spinal stenosis, you can see we found 4% meet the guidelines. So pretty significant impact. We also use that same measurement to look and see, does their function improve after surgery? And here's where the difference between capacity and performance comes into play again. So in this study, we put monitors on people to look at their ability to meet these physical activity guidelines, but we also brought them into the laboratory and we tested their capacity through lots of different laboratory measurements. And what we found was that their self-reported function improved in line with previous research. So this is a representative example of what we know from the spine research literature. In the laboratory, their capacity improved dramatically. Their balance got better, their walking speed improved, the duration that they could walk before they had to stop, either because of symptoms or fatigue, improved 3-4 times. All of these things improved very robustly and highly statistically significantly, but their performance and their monitoring at home didn't change. So, we're a little frustrated by this, but we think that there's maybe a little bit of a story here, and that is partly the old habits die hard. Okay, if you have lumbar spinal stenosis, what happens is that when you stand or begin to walk, the blood flow to the nerves through that part of your back starts to get constricted. And over time, the nerve loses enough oxygen that you get a symptom called neurogenic claudication, and that's where the nerve causes this achy pain down into the legs that makes you have to sit down. And once you sit down, the blood flow reestablishes, symptoms go away, you go back to normal. But this painful condition causes a limitation in your ability to walk. And after years and years of this, we think that people develop bad habits. And maybe that's one of the reasons we don't see improvements in their performance afterwards, because bad habits die hard. So through one of my collaborators, we said, well, let's just see if we can use something simple like step counting to get people to walk more when they have spinal stenosis and see if that makes a difference. And this is not people going to surgery. This is just people with the painful condition. And a lot of people told Christy, who designed this study, that she was kind of stupid for designing a study where you try to get people with spinal stenosis to walk more, because walking limitation is the main feature of the disease. But she said, no, I think there's something to this. And so she developed a lifestyle intervention that was focused around improved nutrition and a personalized step goal over a 6-week program. And this was a low digital intervention. There was a web portal where patients would go to get some nutrition information and where they would get their weekly step goal. And then there was some support through the phone and through a couple of counselors, as well as a web portal for discussion among the enrollees in the study. And over the 6-week program, the participants' personalized goal was to improve their steps by 20% over that 6-week time frame. And these are very sedentary people, like I've described. Their average step counts were around 3,000 to 4,000. And so a 20% improvement meant going from that many steps a day on average, up to 3,600 or 4,800 steps a day. So we're not talking about trying to get people to go from 3,000 steps a day to 10,000 steps a day. That would be a meaningless goal for these people. There's no way they could do it. Just give them a small goal, a 20% improvement. As a group, they achieved about a 15% increase. They didn't quite reach the 20% goal. And as a result of that, they reported better function on their patient-reported outcome measures. Not only that, objective markers of their health showed dramatic improvements, like body composition through DEXA, their lipid profiles. So objective markers of health all showed dramatic improvements just from some nutrition counseling and a very modest increase step goal. So this all demonstrates that using the current methods of activity monitoring, physical activity monitoring, where you look at steps or you look at calories or minutes of moderate vigorous physical activity, we can learn something new about diseases that we didn't know before, such as the capacity of a person improves dramatically with surgery and fixing the problem, but their function at home doesn't change, their physical performance doesn't change. But we can intervene on their performance by simple digital interventions. And so that brings me to kind of the next part of the talk, and that is, getting away from the old measurements, which are physical activity monitoring, and towards what the title of my talk is, which is physical performance monitoring. And here I want to make the distinction between the usual approach of physical activity monitoring and what I call physical performance monitoring. So to help you understand that, I just want to kind of describe the state of the art first of physical activity monitoring. So currently the state of the art, it's been this way for about 15 years. The state of the art in physical activity monitoring is to put an accelerometer, a triaxial accelerometer on a person, and then to measure their activity continuously over a 7-day cycle. And during that 7-day cycle, you don't take the raw data from the accelerometer, because 15 years ago when this process was developed, there was no ability for data transfer and storage to hold the 60 hertz of triaxial data. So they compressed that data into 1-minute measurements called epochs and provided a count per minute measurement. And that count per minute measurement is a summary score of what's happening in the 3 vertices of the accelerometer over the entire minute. And the score for the count per minute can range from 0, which means the monitor is lying on a table and it's not moving at all, up to a little over 35,000. Okay? And then in the lab, those count per minute measurements have been stratified into different activity intensity intervals, which are determined by a thing called metabolic equivalence, which I won't really get into, but those 4 intervals of activity include sedentary, which is from around 0 to 100 on the count per minute scale, light activity, which is from 100 to just below 2,000 counts per minute, moderate activity, which is above the light activity range, and vigorous. And then the moderate and vigorous are kind of put together into one category because that's considered exercise. Anything that you do in the moderate and vigorous activity, you can kind of classify as exercise. Vigorous is intense exercises like going for a run or doing CrossFit or something like that where your heart rate is really going up. Moderate intensity exercises is walking at a rate that's slightly higher than the comfortable rate, where your breathing goes up and your heart rate elevates a little bit. And the assessment of physical activity focuses on moderate and vigorous activity. And so the state of the art is to do that process, I said, and then when you analyze the signal from this, you count the number of minutes of moderate and vigorous physical activity. That's one of the primary outcomes. You count the number of minutes of sedentary time. That's another important outcome. You can also summarize the average daily counts by putting all of the counts together and say, what's your average daily count? Which is largely influenced by what's happening in the moderate and vigorous range, because the counts up here are so large compared to the counts down here where most people spend their time. So the focus of physical activity monitoring is how much exercise do you get. But my patients don't complain about problems exercising. They complain about what happens here. I can't do the dishes. I can't get on the floor and play with my kids. These kind of things. Light activity are the things that bother them. And light activity, this 100 to 2,000 range, is almost completely ignored by physical activity assessment in its current form. And everybody here spends about, if you're being active, meaning you're not sitting like you are right now, once you get up and start to move, 90% of your movement is in the light activity range. So 90% of what people do physically is light activity, but that's completely ignored by the current assessment. And so we had a hypothesis that monitoring physical activity is missing a lot of what happens and probably doesn't tell us about physical performance. And so we went about testing this by using a large population data set called NHANES that has lots of different clinical data on people and includes physical activity monitoring of the cohorts. And the 2003-2004 NHANES cohort also completed a very lengthy questionnaire about pain. Do you have headaches? Do you have neck pain? Do you have back pain? On and on and on, and different details about that pain. So that cohort allowed us a very interesting research environment. And so what we wanted to do is see, can we discover the influence that pain has on a person's daily activity? And even more importantly, are there differences between different types of pain that will influence that? So our first step in that process was to look at the cohort in general and discover everything that we could find that had any influence on physical activity. And the usual suspects kind of came to the top, like BMI, age. Those things had a major impact on a person's physical activity, but there were multiple other health-related variables that also influence physical activity. And we did that because we wanted to control for all of the influencers on physical activity so that we can then later look at the influence of pain. But some interesting insights came from this study where we looked at the influence of things like gender, BMI, age, and other factors on physical activity, and that is that the deflection point where gender, for instance, influences physical activity is right in the middle of the light activity range, not at the edges of the range where we tend to measure things, but in the middle of the range. So the current thresholding likely even misses some of the influences that are happening from these other variables. And it told us that something other than this energy expenditure focus of physical activity monitoring was important in what's happening with people's physical activity. But taking all of that, knowing that we can control for all of the different things that influence physical activity, we then focused on how pain then influences the physical activity spectrum. And this is a heat map displaying kind of the core of this study that we published in PLOS ONE. And what this represents is on the vertical axis, a thresholding of the physical activity scale. So remember that scale from 0 to 35,000? We broke it down into multiple components based on amount of minutes that people tend to spend in different areas of the spectrum. So at the 0 to 1 and 1 to 10 and 10 to 20 range in the very low areas of the spectrum, the intervals are small because people spend a lot of time in there. In the 15,000, and up range where people spend very few minutes, those ranges are much bigger. So we have a proportional division of the physical activity spectrum. And we just did that because we said we want to look more granularly at physical activity. And then across the horizontal axis, we have the different states, pain states that were assessed in NHANES, the 15 different locations of body pain that were assessed through NHANES. And by controlling for all of the other factors that influence physical activity, we then looked to see how pain influenced people's time in these different bins of activity, and then thus derived empirically through this a new thresholding of physical activity that is tuned to see the influence of pain. And if you compare our outcome from this to the usual spectrum, and on the bottom here I have the usual activity spectrum where you have sedentary, light activity, moderate, and vigorous or intense physical activity. That's the normal spectrum. And you overlay that with the output from our assessment, you can see that what we found is if you want to see the influence of pain, you have to look more granularly at what happens in the light activity range. And in fact, we have 3 different intervals of activity that are meaningful in the pain population that all sit almost totally within the light activity range. So we thought this was exciting because empirically the data told us exactly what our clinical intuition was, and that is that the light activity is where the action is at. So we applied this tool even before we published it to look and see an important question about back pain mechanisms. So obesity is associated with low back pain. People who are obese are more likely to have back pain. But why that's the case, we still don't really fully know. Twin studies suggest it's not the weight itself, meaning it's not a mechanical problem that's causing the backs to hurt in folks. And that was one of the primary mechanisms that was suspected. Maybe it's the actual weight of the person on the spine that's causing them to be more likely to have back pain. With obesity, there's certain inflammatory changes and other metabolic changes, so maybe it's a metabolic phenomenon, and that theory has some support through some research. What we did is we said, well, maybe physical activity is the link between obesity and back pain because people who are obese are less active, and people who have back pain are less active than the general population. And indeed, we were able to quantify for the first time that physical inactivity is one of the mechanisms that links obesity to low back pain. And that had been studied through self-report in the past, and no link had ever been discovered. But by applying the tool that we developed, we were able to describe that link and also the strength of the connection and how we might influence back pain for people who are obese. Then we also said, what if we look at this in a different way, and we take this tool and we look at disease populations? Can we use this as a potential diagnostic aid? Can you develop a phenotype based on features from the physical activity spectrum? And so in this study, we leveraged 3 different populations. We used the OAI data set, which is a data set of people with knee osteoarthritis who have had, who've been studied through an NIH-sponsored study. It's a national study at multiple centers. Several thousand people in this data set. We have a lumbar spinal stenosis data set that's been compiled by some of my work here at Stanford and several of my colleagues in North America, both US and Canada, where we've compiled our accelerometry data from lumbar spinal stenosis subjects. And then we could take a pain-free population from that NHANES cohort and use that as our controls. And so we have controls, the NHANES, who have no pain. We have people with knee OA, and we have people with lumbar spinal stenosis. And then we just featureize the activity spectrum based on those intervals that I described earlier. And we found that with a sparse set of features, with 4 different features, we can distinguish between controls with no pain and people with lumbar spinal stenosis with 80% precision. And with 9 features, we can tell a difference between, we can characterize between osteoarthritis and controls. And what was most surprising to me was between the 2 disease populations, knee osteoarthritis and spinal stenosis, both populations who have mobility problems, with 10 features with 72% precision, we can classify people. And that's much better classification than I would have suggested. In fact, I don't have the data to prove this to you, but it's almost a foregone conclusion that you could take x-rays of these same people's knees and x-rays of their back, and it would come nowhere close to being 72% precise in determining who has symptomatic knee OA and who has lumbar spinal stenosis. Nowhere close. And so this demonstrates that looking at the activity spectrum differently, we're able to even potentially provide diagnostic aids. Not only that, if you consider the top 4 features from each of these groups, so all 4 from the first group, but the top 4 predictive features from those other 2 groups, you can see that the vast majority of the features that we derived came from this part of the spectrum, where we thought the meat was going to be in our study in these people with musculoskeletal problems. So that's kind of where we're at in dealing with the old way of looking at activity monitoring, which is to break down the 60 to 100 hertz of data into a 1-minute summary score. But we think that that approach probably lacks some precision because you're losing so much signal when you compress all of that data into 1 minute. So we also want to explore what happens when we look at the raw data from these sensors. And to do that, we developed a protocol where we place sensors in multiple locations, and this is one of the doctoral candidates that spent some time with us. And we had people do multiple functional tests in the laboratory, like a 6-minute walk test or a 40-second walk test, timed up and go, stair climb test, several of the different validated physical functional scores. And during that time, we continuously monitored them at these different points on their body. And we took 3 different populations, knee OA, lumbar spinal stenosis, and then controls that were age and gender matched to our 2 disease populations. And now we actually have a stroke data set as well, which I'm not going to present here. But the stroke group provides some very interesting insight beyond what I'm going to show you now. And to give you an example of what we're doing, this is data from an approach that was developed at EPFL, and I had a postdoc from EPFL spend some time with me through the Stanford EPFL exchange and brought some of their algorithmic approach to analyzing what was happening just from the foot sensors. So only the sensors on the feet, and we're not looking at the sensor on the waist or the sensors on the wrist. This is just looking at the feet. And we're able to break down different spatial and temporal parameters about the gait that are all listed here, even including, down to what's happening at the foot, the toe clearance and what happens during the swing phase of gait. So these are all types of things that you would get from a traditional gait lab, right, which is very expensive and very time consuming for researchers and for patients. And then this graph just simply lists the sensitivity of multiple different measurements we're gathering from the feet. during the different walking tests. So now I'm only looking at the different walking tests that we did in the lab and looking at the ability of the feet sensors to discriminate populations. Here's some preliminary data from this assessment where we're looking at controls, spinal stenosis, knee osteoarthritis, and stroke populations, and looking at some of these parameters from their gait. And you can see, very meaningful differences across these populations from this kind of information. Another graph showing stuff about the temporal parameters from the gait and the populations. This is an assessment that was clinically driven because people with knee osteoarthritis often have worse pain when they start. They have a gelling phenomenon where when they get up from a seated position and they first start out, their knees bother them the most. And then as they move, it kind of loosens up and it becomes a little less bothersome, so they're able to walk a little bit better. And then ultimately, the pain mounts again and causes them some limitation. And that's completely different than the typical pattern of spinal stenosis where somebody stands up, feels good at first, and the longer they're up, the worse they get. So we simply asked the question from this data set, what's different between the first minute of the 6-minute walk test and the last minute of the 6-minute walk test in these two populations? We think it'll look different, and indeed it did. It turns out that the best discrimination for the knee OA people is within the first minute of the walk, but it doesn't change much during the 6 minutes, whereas for the spinal stenosis group, the best discrimination happens at the end of the walk, the last minute of their 6-minute walk. And the first minute of the walk doesn't tell you as much about the disease relative to controls. And you saw something about this recently, but with collaborating through the Neuromuscular Biomechanics Lab and Scott Delp and his OpenSim, we're starting to talk about how we might use this data from the sensors and blend it with advanced biomechanical modeling so that we can develop better clinical applications for these types of tools. So this is the type of thing a physical therapist might be able to use to address a person's specific problem and display that problem to the patient. So just to summarize, where do I think we are in orthopedics right now? Well, using these digital tools, we have the ability to quantify the impact of disease in ways that was not possible before, and in objective ways, and what I think are meaningful ways, and ways that can be applied across the disease spectrum. We're developing new methods that I think are going to be more precise, provide better insights about perturbations of motion quality and actual targets for clinical improvements, and new insights about interventions that will be helpful and more specific to the patient's needs. And then emerging methods to phenotype disease so that we can build these precision health tools in orthopedics that will ultimately allow me to have a better conversation with Jane and tell her what I could tell the NFL player, which is something that's specific to her condition and meaningful to her questions about what her treatment decisions mean for her down the line. So that's been my journey, and I appreciate all your guys' time listening, and I think we have a little bit of time for questions.
Thanks. I'll just kick one off. On one of your earlier slides, you said you had sensors on both the wrists and on both feet and even on the hip. Could you talk a little bit about what was on the hip, and were they like commercial products or sensors that were developed by someone here?
So the monitors we use for that study are research grade monitors, IMUs. But as Mike pointed out recently, the IMU that's in the Apple Watch is every bit the same as the IMUs in these research grade monitors. The only difference really is that the research grade monitors have done some validation around the way they provide the data to you. And so there's some assurance that you're getting a level of quality of data. But the actual sensor itself is the same thing. So ultimately the goal with this kind of research is that we'll be able to implement this in people's normal lives. And I took out a slide for sake of time where I show all of the different sensors and the locations of the sensors that are being commercialized right now. Because of the work I do, I have people from different startups come to me all the time asking me for advice about what they're doing, and sensors are being placed everywhere. I was at the Adidas Advanced Sports Performance Laboratory in Germany just about 6 months ago, and not only does Adidas have sensors already built in shoes like all the other shoe companies, but they actually have an energy harvesting mechanism that they've patented whereby just wearing the shoe creates energy for the sensors. So you can power the sensor for the life of the shoe. So data like this is going to be more and more available. And in fact, we consider that when we design these studies. We say, where are sensors going to be in the future? So where do we need to develop insights and algorithms now so that, 10 years from now, the EMR is going to be fed with analyses that happen in the cloud that stem from the data streams coming from the sensors that people are wearing on their bodies just by fact of putting on shoes or underwear. So.
Your question, your last comment segues straight into the question I have. Firstly, congratulations on the level of granularity you have in what you're doing as far as the human being is concerned. Have you looked at the environmental factors such as walkability of neighborhoods and using ArcGIS data and or gathering data from other sensors to be able to better inform that EMR so that when you make a recommendation to the patient about doing more exercise, you can also tell them where they can go or not go safely?
Yeah, that's a really good point, and the answer to that is yes. So for instance, in the lifestyle intervention study, one of the things that the study did, which I didn't go into, was it didn't just give a step target, but it actually gave people information about where to achieve that. So we assessed their geolocation, and we said, your 5-minute drive from this mall, if you do one loop of the mall, you'll meet your goal. So we gave them very specific information about where they could go to achieve their goals. And I think that you bring up an important point, and that is that, the context of these kind of things have to be meaningful for a person. Not only that, I'm really excited about work that I'm not involved in, but I try to keep up on a little bit, like the use of digital tools to assess mood, for instance. And mood actually is one of the strongest predictors of treatment outcome for orthopedics problems. So if you're going to get a knee joint replacement, your x-ray matters less than whether you're depressed or not in terms of your outcome. And so ultimately, for me to develop clinical decision support tools or algorithms that can be downloaded to an EMR to help the clinician provide more precise care, I got to have information from these other data streams in order to do the best job. Now, I don't work on those things personally out of my lab, but I keep abreast of them because I think it's going to be an important part of the whole ecosystem in the future.
Great talk, very interesting. Just curious, so when you made the relation to NFL players, I mean, they all have similar baselines. If you're a cornerback, you're going to run a 4.40, so you have all this back data to apply to, whereas Jane, she doesn't necessarily have as similar of a demographic, so it seems like a way maybe to have a better baseline for Jane is to sort of, in the future, start instituting preemptive monitoring. So we have baselines on individuals as opposed to retroactively putting them into a data set they may not. And then the other thing that was, I noticed was Jane said she wanted a community to sort of ask about this stuff, which is different than having a community's worth of data. So how do you sort of think about that? Because what I heard was she wanted some personal reassurance that this would work for her, not necessarily data supporting that.
Yeah, those are both really good points. And